Thank you for joining the Combustion webinar today. And today it's our great honor to have Professor Yuyang Li to give a Combustion webinar today. And I guess Professor Yuyang Li is very famous in our community, especially in the community of the reaction kinetics. But just still let me introduce him. And currently, Professor Yuyang Li is a professor and also the vice dean at the School of Mechanical Engineering at the Shanghai Jiao Tong University, which is also a very famous university in China. His research interests include combustion chemistry, flame dynamics, spray and droplet combustion, and industrial combustion, especially for low carbon fuels. Professor Li has a greater publication record, as most of us know, and he has published more than 150 peer-reviewed journal articles with an H index of 35, including almost 100 papers in the Journal of Combustion and Flame, and also Proceedings of the Combustion Institute. And he has received the Research Excellence Award of the Combustion Institute, and then also the Berners-Lewis Fellowship. And he has also served as colloquium co-chairs of the 38th and the 39th International Symposium on Combustion. So a very important and active member in the combustion community. So Professor Li, the floor is yours.
Okay, thank you, Li, for the introduction, and also thank you, Professor Zhu and Professor Han Wang for the invitation. And it's my great pleasure to give the presentation here today. And my topic is related to the fundamental combustion research of low carbon fuels, and mainly focusing on understand, predict, and regulate the combustion chemistry of these fuels. And here is first to give some motivations. And actually, as we know that the whole world is now working together on reducing carbon dioxide emissions and pursuing a better and cleaner living circumstances. As we all know that it's almost 200 countries have signed the Paris Agreement and up to now. And actually China is also one of them. And recently, especially in the year before last year, China peaked to achieve the carbon peak emission peak by 2030 and carbon neutrality before 2060. And also for the Shanghai city, we want to achieve the peak before 2025. That is 5 years earlier than in the whole country. And as we all know that China actually becomes a developing economy and now has almost 1/3 of the global carbon emissions nowadays. And therefore, it's a very huge task for China to reach these targets. And therefore, nowadays, for both China and also the whole world, low carbon fuels are attracting much more enormous concerns than we ever had. And as we all know that fossil fuels like natural gas, gasoline, and kerosene and diesel oils, they are actually dominant fuels nowadays for those power machineries like internal combustion engines, stationary and aero gas turbines, and so on. Therefore, to replace the fossil fuels, we need to use low carbon fuels, which are mainly synthesized from biomass or capture CO2. For example, the renewable synthetic fuels, and will become the main source of power machinery fuels in the carbon neutral future. And we can see that actually we're using the low carbon fuels, for example, in the distributed energy supplies, and then just supply energy for the city in the future. And also for those renewable synthetic fuels from mainly from the carbon dioxide and also water, and then we will use solar energy or other energy sources and renewable energy sources. We can generate a lot of new fuels compared with the fossil fuels. Therefore, this is a very bright future, but we still have a lot to do nowadays. For the combustion chemistry of these low carbon fuels, which are most of them are quite new for the whole community. And we need to have a better understanding of the combustion characteristics. For example, taking for the ammonia and its fuel blending for the laminar burning velocity data, which is very important data. And as we can see that actually before 2020, we only have the highest pressure up to 5 atm, and there's lack of higher pressures, especially for the engine relevant pressures, like in the internal combustion engine or gas turbines, which is generally over 10 atm. And also, to pursue the digital design of power machineries, we need highly predictable kinetic models of low carbon fuels, which covers a wide range of pressures, temperatures, and equivalence ratio conditions. And those we call it widely applicable and highly predictable kinetic models, which is our main target to develop and then applied in the numerical simulations. And also for the novel fuels like ammonia and also other fuels, we can see that their combustion characteristics are very different from the traditional fossil fuels. And we can see that, for example, for ammonia and air mixtures, its laminar burning velocity is quite slow compared with methane air or propane air flames. This makes the combustion of ammonia quite less stable compared with this fossil fuels combustion. And therefore, we need to consider how to regulate their combustion chemistry, like combustion enhancement, and also how to control the emissions of these fuels. So for the first part of my talk, I would like to introduce our effort in understand the combustion chemistry of the low carbon fuels. First, from the global combustion parameters, we have laminar burning velocities, which is a very important parameter, as well as an indicator of combustion intensity. And as we can see from this figure, that is the literature research for the LBWs of normal alkenes. That is mainly this photo was taken this figure was made in 2017, and we can see that actually for the transportation fuels and also for the engine relevant pressures, we have rare data to measure for these fuels. This mainly results from the methods we are using. For most of the measurements we are performed are based on the flame, on the burner. For example, like a counterflow or stagnation flame and flat flame, benzene flame, or heat flux burner. And all those flames will be strongly influenced by the instabilities at high pressures. Therefore, their measurement range are mainly focused on the normal to elevated pressures. And then to measure the high pressures, we mainly use the spherically propagating flame. And as we can see that using this kind of research, actually we can reach very high pressures. But then what's the reason for the limited data in this engine relevant pressures and for the transportation fuels? This is mainly because for the conventional combustion vessels we are using, like the single combustion chamber vessel or dual chamber vessel, they have their own limitations. For single chamber vessel, many designs adopt a window which is mounted at the outside, and this will make the window easily leak or broken at high pressure. And then for the dual chamber vessel, we can see that actually the inner chamber can hardly be directly heated. This makes it quite difficult to measure the high boiling point fuels. Therefore, for the single chamber vessel, then high pressure measurement will be quite difficult. And then for the dual chamber vessel, the measurement for the high boiling point fuels will be difficult. And therefore, we based on the single chamber vessel, then we use the new design to make the window to be mounted from the inner side, and this can make the window sustain very high pressures. This mainly we can reach up to 200 atm after combustion, and this can be converted to almost more than 20 atm before combustion. And also the single chamber has a very simple design, and it's very easy to be heated up to even more than 500 Kelvin. And therefore, with this self-sealing and the dual surface protection design, and we can reach to high pressure measurements for those high boiling point fuels. And this is a diagram for the apparatus, and we're using a pre-mixing vessel and also a high pressure combustion vessel, and also with a Syrian method to take the flame images. And also for some special fuels like ammonia, we can use passivation method to reduce its absorption. And then the data was evaluated with the nonlinear extrapolation method. And also because it's a single chamber and that is a constant volume chamber, and therefore we have to take the upper limit of the flame radius to up to 23 millimeter, which is smaller than 0.3 times of the chamber inner diameter. And this can reduce the influence of the confinement effects. And also we performed the uncertainty analysis for the data using the Morpha method. And here we can see that for ammonia and hydrogen mixture, and we can measure up to 10 ATM. And this just shows us very good flame images. And also we measure laminar burning velocity for both hydrocarbon fuels and also for the low carbon fuels like N-butanol. And this is up to 20 ATM for N-butanol, and it's mixture with air and also with oxygen and helium mixtures. And also we can also observe the flame images, and then we can find also the transition from the weak flame surface to the strong flame surface for the 2-butanol, oxygen and helium flames. And also we can interestingly find the pulsating instabilities, which is traditionally observed in the gas phase fuels because of the difficulties in measuring those liquid fuels. But it should be there. But then this is almost the first time to take the flame images for those pulsating instabilities of liquid fuel. And also we can get the pressure dependent coefficient of helium-doped flame. And then we can also observe that it's weaker than air flames. That's just some examples to show that the method can measure those fuels with boiling point higher than 100 degrees Celsius and at pressures up to 20 ATM. And also we can have some findings about the cellular instabilities, and example for methanol air flame. And if we just measure it up to, for example, the equivalence ratio 1.6, we can find the cellular instabilities increase. But then if we go on to measure its equivalence ratio to 2.0 and very rich flames, and we can see that the flame becomes smoother. And this shows a non-monotonic change of the cellular instabilities. And we also performed the instability analysis for it. And we find that actually the controlling effect for the cellular instability is a critical practice number, and it decreases with equivalence ratios until 1.6. The equivalence ratios up to 1.6, and then the change becomes quite smoother, quite gradual. And then another factor that can influence the instability is the flame thickness. Then with the equivalence ratio higher than 1.6, and we can see that the flame thickness becomes thicker and thicker, and this can stabilize the flame. Therefore, these two effects will have a combined effect, and then will make the flame has a non-monotonic effect with the cellular instabilities for the methanol flames. And another method we use is synchrotron, and this is a collaboration with Professor Fitchi. And we can see that with the synchrotron and Hefei, and we can take the photoionization mass spectra, and that is just like a measurement of the weight of the molecules. And but for the molecules with the same molecular weight, and we can also take the photoionization efficiency spectra, and this is like a length scale or high heat scale. So we can have the two-dimensional informations, both the molecular weight and the ionization energy. That can help us to distinguish the different isomers. And then from 2014, as we have developed the synchrotron beamline in Hefei, and also we further developed the sampling method from the two-staged differential pumping system to the first stage sampling. But this will greatly increase the increase the signal. But then we also found that because the background pressure is very high, and this will cause some disturbance to the measurements. And then we just return to two-stage sampling, but then we also greatly reduce the distance from the sampling point to the ionization point, which is similar to the one-stage sampling. And this can help us with both higher ion transfer efficiencies, better signal-to-noise ratio, and also stronger radical detectability. And also we can prevent the strong influence of the background pressure in the first stage sampling. And this is the design that has been used up to now. And with this update in the method, and we can have some different measurements. For example, first we can see that in the previous studies, that is the collaborative work with Frederick Barton-Leclerc's group, and we can find that actually even we measured a lot of hydrogen peroxide in 2010, and we cannot observe the RO radical, the peroxide radical. But now with updated method, and we can measure the radical, for example, like the methyl peroxide radical, and this can observe the signals. And also we measure the photoionization efficiency spectrum, and we can see that it agrees well with the Frank Condon fit by Maloney and his co-workers. And this proves that the observed signal, this small peak, belongs to the methyl peroxide radical. And then we can also take the signals and mole fractions of these radicals, and then we can compare it with simulations, which can help us to provide guidance for the models, that if we can capture the formation and the consumption of these radicals. And also we perform the measurement at normal pressure flames, for example, in the cold flow flames. And previously we are using a probe, and this will quench the radicals during the long distance of the transport of these radicals, and therefore we cannot observe these radicals. And then also in Hefei, we met the update of the sampling nozzle, and we're using a nozzle instead of probe, and therefore can form a molecular beam. But we have to be very careful because the nozzle cannot be at a very high angle, co-angle. So then we use a small co-angle, for example, like 15 or 18 degree. And therefore this can prevent the disturbance of the flame, and also we can generate a molecular beam. And this shows that we can observe some radicals now in the cold flow diffusion flames, especially those large radicals like aromatic radicals, indanial, and other radicals, which are very important pH precursors. And also here at Shanghai, and we also try to sampling soot from cold flow flames. Previously, we have a lot of other methods to sampling soot, but it can be very difficult to get a very efficient sampling with soot particles, and also with low disturbances. And therefore, similar to the Hefei apparatus, we also use the cross nozzle with a 30 degree cone angle. But then to prevent the disturbance to the flame of the nozzle, then we make a capillary-like stage at the first, and it has to be very carefully designed to not make it too long or too short. And therefore, we can just get very efficient measurement of the soot particles from cold flow flames at different positions with high collection efficient, which will be collected in the Teflon field. And also then we can prevent the disturbance to the flame to a very large extent, that it was quite similar to the probe. And you can see that with directly nozzle, then this will be quite strong disturbance to the flame. Then with the capillary-like stage at the tip of the nozzle, and we can prevent the disturbance greatly. And then we can also ensure because the capillary-like stage is not too long, and then we can prevent also greatly reduce the secondary reactions inside this channel, and therefore this can make the sampling of the soup very efficient and being less disturbed by different factors. And we can also you can see that is TM images of the soup particles sampled from the flame, and we can observe their structures here, and there are many samples at different positions. And then we, because we can get almost milligram scale of soot particles very quickly, and then we can perform the thermogravimetric analysis and also DTG analysis of the soot particles under oxidation conditions. And we can find that actually for those soot particles sampling at the very low positions, and it shows the dew peak characteristics. Then for the soot particles sampled at a very high positions, and we can see that they are only a single peak. And for the single peak, it's mainly the oxidation of the carbonaceous species. And then for the soot particle sampling at the early stage, and we can see that those are mainly those structures related to the nascent or the very young soot structures or the groups on it, and they were after they were just decomposed from the surface, and then can find the first peak. And we also developed the distribution of activation energy model to describe the different activation energies based on the result. And we can see that the method can well capture the measured results. And we can see also for the first peak, it appears at low positions, and also the activation energies almost 20 kJ per mole lower than the carbonaceous species. That shows us strong difference between the first peak and second peak, meaning they are coming from different fractions in the soot particles. Then we can, with those, better understand those actually the combustion characteristics and also the chemical structures of the flames. We can try to develop kinetic models for the prediction of combustion chemistry of the low carbon fuels. And here we shows that actually we can, in typical fuels, we have the small mechanism for the C0 to C4 mechanism, and also we have the fuel sub mechanism. And this also the pollutant formation mechanism. And here shows the model construction, and we have the first for the pyrolysis mechanism for those core mechanism, and we developed the pyrolysis mechanism based also on special attentions on the methyl-related groups chemistry, and also we have the CO formaldehyde and methanol mechanism, which is mainly focused on the HCO and the CH2OH related reactions. And also for the methane and the C2 mechanism, we focused on the intermediate to high temperature mechanism. And then for the nitrogen mechanism, we also focused on the high temperature mechanism of ammonia. And here shows the updated reactions in our models, and it's mainly from the ammonia to syngas to C1, C2, and C3 mechanism. For the co-mechanism we have right now we just focused on. And also for those larger fields, here just take an example of cyclohexane, which is hydrogen carrier and also hydrocarbon. But with just showing examples that we recently performed very detailed analysis on the calculations and analysis on the low temperature oxidation of cyclohexane, especially for its first and second oxygen addition mechanisms. It shows the quantum chemistry calculations we performed for the second oxygen addition, and then we also performed the inverse topolarization analysis. And we found that actually the conformers have strong influences, and therefore we have to simplify the system. And if we want to really think about the conformers, so we use the Boltzmann distribution determinations to get the distributions of each type of the conformers. So we can simplify the conformers to 5 types, and so 4 types, and we do not need to just consider this is almost 23 conformers. So we just simplify them as 4 types. And then eventually we can get the rate constant for this. And it has to be mentioned that actually this is just the very first step to investigate the cyclohexane oxidation mechanism, and there's still some further works need to do to improve the accuracy of the theoretical calculations, because those large systems are really difficult to calculate. And here shows the validation of our models. For example, here shows the syngas and natural gas model, and we performed this the simulation for the different kind of experimental data like ignition delay time, burning velocity, and species profiles. Here also shows validation condition range. It covers a wide range of pressures, temperatures, and equivalence ratios. And also this is for ammonia and for burning velocities, species, and also ignition delay times. It's just showing some as an examples. And also we validated our model with special interests on the very specific reactions. Here shows the reactions of the methyl radicals, oxidation, and especially nowadays in the co-mechanism, we are very interested in validating the model for the methyl oxidation reactions on the intermediate to low temperatures. But previously for the mission combustion, because itself is very difficult to have oxidation on the low temperature conditions, low to intermediate temperature conditions, we need a high temperature to initiate the methyl formation for the pure methane combustion. And therefore, we propose that we can use the oxidized, oxygenated fuels. For example, here we take in the pyrolysis, under the pyrolysis conditions, and here we can see that we use this molecule with a very weak bond here, and then we can break it and with acetyl radical, and then we can easily decompose at here, and we can get the methyl radical, and we can then react with with further reactions. And then for the oxidation conditions, we use acetaldehyde, and it is also very easy to have the low temperature reactions, and then it can also very easy to form the acetyl radical, and acetyl radical can then decompose to methyl radical. Under these conditions, then we can have a lot of oxygen, and then the oxidized reactions, oxygen addition reactions happens for the methyl radical under low temperature conditions. And then here we can get the result, as we can see that this we showed before, that we can get the methyl peroxide radical, which can guide us for the reactions between the methyl radical and the oxygen. That is the first oxygen addition reaction of methyl radical, and it's strongly related to the form of the methyl peroxide radical. And also for the acid, which is also strongly related to the low temperature oxidation. And we can see that we also performed its research in the combustion vessel. And because acid actually is very easy to be absorbed on the surface of the stainless steel, and therefore we have to perform the surface passivation. And we can see that with different rounds, and eventually we can finally get for both acetic acid and also for the propanoic acid, and we can get for also after 3 round measurements, we can get very quite stable data repeated, and then we can get the laminar burning velocity results. For example, at 423 Kelvin for the 2 acid fields. And then we can also perform the modeling analysis for it, because we can simulate them and then perform modeling analysis, predictions of the radicals. And you can see that the two acids, even there, one is C2 and C3, they're quite similar with molecular weight, but still they have quite different radical production abilities, especially for the hydrogen production, and it differs too much. And then we also perform the rate of production analysis, and we find that actually because of the actual tracking products of the two acids they have different decomposition pathways. For the acetic acid, and its radical will mainly decompose to methyl radical, and therefore you will have a lower rate laminar bonding velocities, and also because methyl formation will high concentration of methyl radical will react with hydrogen, and for the chain termination, and therefore it's the concentration of hydrogen atom is also quite low. And then for the larger ones, like the propanoic acid, its radicals can be readily decomposed to those reactive radicals, and it can further increase its laminar bonding velocities, and also make the formation of hydrogen in these high concentrations. And here shows the sensitivity analysis. I will not go to too details about this. And also, we can also use the combustion vessel for the outwardly propagating flame method to do more things. And here shows the interaction between ammonia and NO. And their interactions is very important in both ammonia combustion and also in thermodynamics chemistry. And I think a lot of scientists have paid attention in the thermodynamics chemistry, which they will use the flow reactor or the jet steady reactor to measure this chemistry at quite intermediate temperatures. But nowadays, with applications of ammonia combustion, and we all know that this reaction is very important because ammonia has very big problems in NOx formations. And we can understand the interaction between ammonia and NO at a flame, especially under flame high temperature conditions, it will be more helpful for us to use ammonia. And therefore, by adopting NO as the oxidizer, and we can see that we can use we can use the measurement of the burning velocity, laminar burning velocities of ammonia, NO mixtures to study the interaction between ammonia, because we replaced oxygen with fully NO, and therefore it has no reactions between ammonia and the oxygen. We can have only reactions between ammonia and NO. And we can see that actually the analysis for like the sensitivity analysis and the rate of production analysis both show that in the ammonia and NO interaction, and the most important reactions are the ammonia radical NH2 and reactor with NO, and it has two competing reactions, one forming NH, one forming N2. Therefore, we can see that the reaction forming NH and OH is a very important chain branching reaction, and it dominates the chain branching in the ammonia NO reaction system. And here we can find that we avoided the influence of the H plus O2 reaction in this system because we have no O2, and we have the NH2 with NO forming NH and OH has the largest sensitivity coefficient and positive sensitivity coefficient. And then its competing reaction, NH2 plus NO forming N2 and H2O, which is chain termination reactions. It has the largest negative sensitivity coefficients in this system. And we can also find that predictions of previous models show fairly broad distributions, and therefore we had to develop the kinetic models to make it better capture the results. And this figure just tells us that actually the laminar burning velocity experiment of ammonia, NO, and also this nitrogen mixtures using the outwardly propagating spherical flame method can provide highly sensitive validation targets for the kinetics in ammonia and NO interactions. And interestingly, you can see that if we just increase or decrease the most important chain branching reaction R4 by 15% or increase or decrease of the rate constant, you can see that the model predictions change greatly, which is much broader compared with experimental uncertainties. That also proves that the system is quite sensitive to this reaction. And then similarly, if we just tune the rate constant of R4 for 15% from the in the ammonia NO flames, which is measured by Wendering and his co-workers in 1994. And we can find that actually the flame data doesn't change too much. And also, especially for the very important fuel and the NO profiles, they just change in the positions a little bit of the profile, simulated profiles. And we all know that the simulation profiles of the fuel and the oxidizer, actually in the laminar premixed flames, are strongly influenced by the accuracy of the temperature profiles. Therefore, the small change of the simulation results will be easily influenced by the uncertainty of the temperatures. So it can be very difficult to validate the targeted reactions using the laminar flame speed with speciation data. But then the laminar burning velocity data can provide very sensitive results. And also we find that actually the previous used rate constantly in Syriza model, which is also firstly adopted in our model. It is taken from the work of Miller and Global, and it was multiplied by 1.65 times in the original source in the Syriza model. But based on the new validation, we find that we can adopt the original key. That is, the solid curve adopts the original key from Miller and Global work. So this is also quite interesting that the laminar burning velocity data can give very strong constraint for the specific kinetics, and if we adopt the strategy of replacing the oxidizer. And then we can further play with this strategy to other systems, for example, for the hydrogen and NO interaction. Because nowadays we all know that actually hydrogen combustion also influenced with high flame temperature and also high NOx emissions. Therefore, hydrogen NO interaction is also very important. And we can also re-examine this interaction using the burning velocity experiment of hydrogen and NO, also can also with N2 to just do this work. And here also shows the results of the experiments and also the simulations. We can also find that previous models shows very broad distributions, which is much higher than the simulated than the measured results, both for the hydrogen NO fuel system and also hydrogen NO and N2 systems. And also we performed the rate of production analysis. We find that the most important reaction, chain branching reaction, is H plus NO give us N and OH for this reaction. And then we also performed the evaluation of this reaction. We find that the evaluated rate constant from Barker and his co-workers in 2005 is quite good, and this behaves quite good. But then if we adopt other sources, we can see that the model performance will change greatly, which is also much higher than the simulation and then the measured uncertainties of the experimental data. And similarly, we can also go to see the missing NO interactions, and this can also be important because missing and ammonia mixtures, missing and ammonia mixtures also very broadly adopted strategy to enhance ammonia combustion. Then we can also expect very strong NO emission formations in that system, and therefore missing and NO interactions will be also important under flame conditions. And this can also be characterized by the LBV experiment of missing and NO experiments. And then we can find that in this system, the very important kinetics is both includes the hydrogen NO interaction and also for the methyl radical and NO reaction. So this is a very typical missing NO interaction kinetics. And we can see that especially under the rich conditions. And therefore we can find that for the hydrogen NO interaction in the missing NO reaction system, it will decrease as the equivalence ratio increase from, for example, 0.6 to 1.8. And then the missing chemistry will become more and more important because we have higher and higher missing concentrations at the rich conditions. And therefore it will have a higher scientific coefficient as the equivalence ratio increase. Sorry, this is wrong, this should be increased. Okay, so we have introduced a lot about the predicting the combustion chemistry of the low carbon fuels. And we can see that actually nowadays in Shanghai Jiaotong University, we have performed a lot of work in focusing on both the hydrocarbon fuels and also for the low carbon fuels, especially the syngas and also for the ammonia and methanol and also larger ones, oxygenated fuels. Okay, and for the last part of my talk, I will introduce our effort in regulate the combustion chemistry of low carbon fuels. And actually, there's a lot of work focusing on regulating the combustion chemistry based on different strategies. And here I give a very brief introduction about the principles and why we can use these strategies. And it's quite simple. And we have a global reaction of combustion. That is the fuel plus oxygen and producing the products which can generate heat. So it's quite simple. It's middle school knowledge. And then this is college knowledge. So we can have the reaction rate equation. And the formation of the product equals to the rate constant, and also it's sum with it's product with the fuel and oxygen concentration, and also with the reaction time. Okay, so with this simple equation, so we can see that all of our, most of our regulating strategies can be explained using this equation. So we can vary the fuel components, and this can give the different concentration of the fuel and also different rate constant. We can also vary the oxidizers. So we can also change our oxidizer concentrations, or we can also change the rate constant. And then we can also vary the flow or mixing regime. This can also influence the rate constant, and also can influence the reaction time. And then for if we vary the fuel components, we can co-fire with the reactive fuels. For example, for ammonia, right? We can co-fire it with hydrogen, with methane, with other fuels, with syngas and others. And also we can have the few molecular structure effects. So different, for example, like the isomeric effect, the same molecular weight, the same chemical formula, and then with different structures, you have very dramatic difference in the combustion characteristics and also reactivities. And this is just about how to get the results of regulation combustion chemistry by varying fuel components. We have different methods. And also for the oxidizers, you can have a lot of things to do. For example, as I introduced using nitric oxide in my last slides, that is also we use other oxidizers. That is also we vary the oxidizers. We can also get a lot of new results from it. And then we can also use oxygen enrichment to enhance the combustion, for example, for ammonia. And this is just the oxidizer strategy. And also we can use different kind of flow and mixing regimes. So I will not go too deep to this part. But then we can see that this covers almost all strategies besides those plasma, except for those plasma and other things. But for most of things, if we are using the fuels oxidizers, and it's just related to this equation. I will give a very several examples, especially for ammonia. And we all know that ammonia is a very important future hydrogen carrier and also a future fuel. And this is because it has, for example, it has first the no carbon feature, and therefore it's zero carbon dioxide emissions. But then the most important thing is that it has a high gravimetric hydrogen density and also highest volumetric hydrogen density, as shows here. And it is even higher than liquid hydrogen. So make ammonia a very promising hydrogen carrier and also a fuel. And also, as we know that ammonia has a well-established production, storage, and transportation infrastructures, especially in China. And it's almost the biggest country to generate hydrogen and ammonia in the world. And then ammonia also has been adopted as test fuels for stationary gas turbine and marine engine. Here shows work from Professor Kobayashi, and here shows their efforts in using ammonia as a fuel in Japan. And also recently, it's very popular for the internal combustion engine research field to discuss about the possibility of using ammonia in diesel engines, especially for the marine engines, for the big tank, big ship. But for the ammonia, we all know that it's not a perfect fuel. It has a lot of challenges in ammonia combustion and its applications. First, the very challenging thing is that ammonia has very high energy consumption during its synthesis. So therefore, burning ammonia with current technology is not economic. We have to imagine that in the future, we can use the renewable electricity generated electricities that can provide much cheaper electricity, and then can help us to make the generation of hydrogen and also ammonia much cheaper, and then we can use ammonia at last. And the second challenge is that ammonia combustion has very high NOx emissions during combustion. And if you do nothing in ammonia combustion, the formation of NOx can be quite huge, especially under the lean conditions. But nowadays, actually, people have performed a lot of efforts in controlling the NOx emissions in ammonia combustion based on, for example, the staged combustion strategies, and also with the DeNOx catalyst strategies. And it can have a very good control of NOx in many test apparatus. And we believe that this will be solely controlled effectively. And the last one is about the low combustion intensity compared with other fuels, as I have showed this figure before. And we all know that ammonia is quite slow, has a quite slow flame propagation. Therefore, our work focused on the last challenge, how to enhance the combustion of ammonia. And we all know that actually in previous studies, people mainly taking co-firing strategy and to enhance the combustion of ammonia. But beside hydrogen, also some renewable sources of the fuel. But if you are using natural gas and other sources, and you have to face the challenge of carbon emissions, that is unavoidable if you are using natural gas or other hydrocarbons to burn it. But even you use biofuels, but still you can generate carbon dioxide. Therefore, that is also a challenge for the co-firing strategies. Therefore, we can consider about more strategies. And here we have three strategies: the co-firing with other fuels, with reactive fuels, oxygen enrichment strategy, and also we can pre-crack ammonia and get ammonia, hydrogen, and nitrogen mixture in a fuel tank, in a fuel pipe, and then mixed with air. And this three strategy has been actually studied in our group, and we would like to understand deeper inside the three strategies. The first, we all know that ammonia air flame has a very low flame speed, and therefore they are greatly affected by the buoyancy instability. And we can see that for the ammonia air flame, buoyancy effect is quite strong. And then with three strategies, they can all control the restrain the buoyancy effect, even on the elevated and high pressures, still showing very spherical flame, and also the buoyancy effect doesn't lift the flame too much. That means the flame propagation has been accelerated greatly. And also because we have performed the study of ammonia up to 10 atm with a mixture of syngas and also with pre-cracking strategies. So we find that the flame propagation of ammonia and the blends at 10 atm have strong cellular instabilities under the lean and stoichiometric conditions. And this is quite similar to the small fuels like hydrogen and also methane. And then we derived the laminar flame speed, laminar burning velocities from the flame images. This also tells us that with the three strategies, the laminar flame propagation can be greatly enhanced, even up to the scale of methane that is reached to 3 centimeters per second, and also can reach higher if we just using further increasing the content of these strategies. And then our model can reasonably predict the laminar burning velocities in the three strategies. We can capture all the measured data. Then deeply, we want to understand the controlling effect in the enhancement strategies. As we know that we have three effects. That is the chemical effects, thermal effects, and also transport effects. And in most cases, chemical effects and thermal effects will be the dominant effect for the combustion enhancement. Then we looking inside the adiabatic flame temperature of the three strategies. We find that the three enhancement strategies all dramatically elevate the adiabatic flame temperature of ammonia. And we can see that, but the extent is different. For the oxygen enrichment, it has the highest enhancement of the adiabatic flame temperature compared with other two strategies. But then if we are looking inside the reaction network of ammonia consumption in the three enhancement strategies, we can find that they are quite similar. And therefore, this tells us the thermal effect of ammonia enhancement strategies are coming from the increased flame temperature, and the chemical effects are mainly coming from the enhanced of the radical production. But how the question is how to distinguish thermal effect and the chemical effects in ammonia combustion with the three enhancement strategies. As we all know that it's very popular to use fictitious diluent gas method to separate the chemical effect and the thermal effect. This is also principally coming from this equation. Laminar burning velocity is strongly related to this this term, and we can see that the chemical effect is mainly related to the activation energy, and then the thermal effect is strongly related to the adiabatic flame temperature. But then if we want to separate them, we have to make the gas mixtures kept with a constant adiabatic flame temperature. This will also with the same transport properties to make us separate the chemical and thermal effects. That's why we use fictitious diluent gas method. Because in the traditional fictitious diluent gas method, for example, for hydrocarbons and air combustion, and because nitrogen is diluent gas, therefore we can replace part of nitrogen with FN2, and then we can use some larger heat capacity molecules like carbon dioxide to replace it, and to use this heat capacity or also thermodynamic data for the FN2 species, but then FN2 has the same transport data as N2. And also we maintain the oxygen mole fraction. So this can help us to separate these chemical and thermal effects in the conventional hydrocarbon combustion with the enhancement or other strategies. But then the problem in the ammonia combustion is that with the conventional fictitious diluent gas with CO2 as a thermodynamic data source, and because actually nitrogen is a product instead of simple diluent gas in ammonia combustion. If you replace too much content of N2, then you will cause strong shift of chemical equilibrium in the ammonia combustion if you use FN2, CO2. And this will cause separation of the chemical and the thermal effects quite problematic. And therefore, we propose that in ammonia combustion, for the fictitious diluent gas method, we suggest we can use the high molecular weight molecules, much higher than carbon dioxide, and with a lot of bonds. Therefore, we have these molecules has a very high heat capacity. This can help us to minimize the influence of chemical equilibrium. For example, we can use the chlorine. This C24H12 has a lot of bonds, and therefore its heat capacity is about 23 times as that of nitrogen at 2075 Kelvin. This is typical flame temperature. By using this strategy, this updated method, we do not need to separate a lot of nitrogen in the system. It's just 1 or 2% of nitrogen replaced, And this can minimize the influence of the shift of equilibrium and can help us very accurately separate the chemical and the thermal effects. And here shows the result. We can see that we can get the governing effects in the enhancement strategies. And we find that actually in the oxygen enrichment strategy, because the reactants don't change, and therefore the thermal effect plays a dominant role in enhancing ammonia combustion. As we know that it's almost 400 Kelvin increase in the adiabatic flame temperature. So it's quite a large increase. Therefore, it's mainly governed by thermal effect. And then in other strategies, the chemical effects and the thermal effects are both important for enhancing the ammonia combustion. But then if we go deeper, looking deeper inside the comparisons, we find in both co-firing and pre-cracking strategies, the chemical effects play a more important role. And also we compared with the pressure effects of the laminar burning velocities. And in all the three strategies, the laminar burning velocities will drop as the pressure increases. That means we have slower flame propagation on high pressures. It's similar with other systems. But then compared with syngas co-firing, pre-cracking, and also other hydrocarbon combustion, and the pressure dependence of ammonia, oxygen, and nitrogen combustion is mainly pure ammonia air combustion, and also for the ammonia, the oxygen enhancement combustion of ammonia for systems. They will have weaker pressure dependence, and this is mainly due to the reduced importance of the three-body chain termination reactions, and this will also indicates that the oxygen enrichment of ammonia combustion will have can better preserve the laminar propagation on the high pressures. And we also do simulations for the NOx formation in the pre-cracking strategies. And we can find that actually with the increase in pre-cracking ratio of ammonia, and the NO mole fraction will first increase, but then decrease. And the peak locates at almost 70%. And then by performing the modeling analysis, we can give the reasons for this phenomenon. Also, we can find that actually this effects is only slightly influenced by the thermal effect, but mainly caused by the chemical effects based on the fictitious diluted gas method, updated method. And then we can see that actually in the modeling analysis, we can find that actually the strong synergy in between ammonia and hydrogen were causing the unmonotonic trend of the NO formation. And this is mainly because for the NO formation, the NH and H radical plays a very important role. And we can see that here shows the NH radical profile, and this is H profile with the increasing pre-cracking ratio. And then if we multiply them together, and you can see a similar trend happens with NO formation. And the strong synergy in NO formation between ammonia and hydrogen will cause greatly improved NO formation in the pre-cracking. And also, this is similar to the ammonia and hydrogen co-firing strategy. So in both strategies, they'll be influenced by the synergy between ammonia and hydrogen. So that indicates that if we are using the hydrogen enhancement, co-firing hydrogen to enhance the ammonia combustion, we should be very careful about the ratio of hydrogen in ammonia combustion, because it will cause greatly enhanced NOx NO formation. And also for these strategies, we also tested them in model combustor at Shanghai. And here shows our model combustors. This is the normal pressure and temperature model combustor, which has an airflow rate up to 20 grams per second. And we can also have elevated pressure and temperature model combustor up to 0.5 kilograms per second. And we also use the lasers to diagnose the system. Like we use a high-speed camera to get the chemiluminescence, and also we get the lasers to get the PRV and the PLE for OH, formaldehyde, and also NO to be measured. That shows our systems in Shanghai. And here shows the images shows the flame with co-firing with DME, and also with oxygen enrichment. And we can see that actually the flame will gradually shrink as either the reactive fuel content or the oxygen content increases. And that means the flame becomes stabler. And different colors in co-firing with DME under lean conditions result from the different chemiluminescence, and we can find different colors, and which denotes that preferential DME and NH3 ammonia oxidation happens at lower and higher regions. And then the rose gold color on the stoichiometric and slightly rich conditions in the DME co-firing denote that most simultaneous oxidation of DME and NH3 will happen under these conditions. And then if we look into the lean blowout limit, LBO, and we can find that it decreases remarkably as the reactive fuel content or the oxygen content increases. This indicates that the flame becomes more stable. And this is also strongly related to, associated to the enhanced reactivity of the reaction system. We can also see that they increase the laminar burning velocities with it. But then we also observed that the emissions of NO and NO2 both increase. And this shows the trade-off behavior between the combustion enhancement and the NOx emissions. And therefore, for better application of ammonia combustion, especially with those enhancement co-firing with hydrogen and other reactive fuels, we should be very careful about the NOx emissions and find better controlling strategies for these emissions and better strategies to get to reduce the trade-off effect. And also, we show another simple example about the enhancement of the biogas system, which is mainly composed of methane and carbon dioxide generated from the biomass feedstocks, and then we enhance it with DME addition. And this shows the flame images, and we can see that with the increasing ratio of DME and the flame, especially in the high temperature range, in the flame zone, we can find the more and more stronger purple color. And this is mainly coming from the chemiluminescence of formaldehyde. And we can see that DME can easily generate a lot of formaldehyde, as we know. And also based on the kinetics calculations using ChemKing, we can find that with increasing DME content, it's almost 10 times higher of the concentration of DME. And the numerical simulations using the CFD tools also shows us that with increasing alpha, that is increasing DME content, we have stronger and stronger concentrations of formaldehyde. And then if we perform LBO measurement, we can also find that actually with the addition of DME, this greatly enhances the combustion, and the LBO decrease with the increasing of the DME content. And this is strongly related to increased flame temperatures and also the reactivities. And we can see that both the ignition delay times and laminar burning velocity is showing that the reactivity of the system becomes stronger and stronger as the DME content increase. So this can also help us to understand the reason for the DME enhancement. It's both co-working or co-collaboration of the thermal effect and chemical effect. And then with increasing adiabatic flame temperature, then the measurement shows us that the NO emissions become also larger and larger with increased DME content. So this also shows a trade-off effect of between the combustion enhancement and also the NOx emissions. So we should also be very careful to be aware of this enhancement, increased NOx emissions, and consider better strategies. So here I give a very brief conclusions and perspectives. And combustion of low carbon fuels in power machineries will play a crucial role in the carbon neutral future. And this trend, as we can all know, that is almost inevitable happening, and we have to just better understand the combustion of low carbon fuels to make us prepared for this upcoming era. And there is still a long way to go for a deeper understanding of the combustion chemistry of low carbon fuels, because though these fuels are too many, and we have a lot of limited knowledge. We have very limited knowledge for their chemistry, their reaction rate constant, and so on. And therefore, advances in experimental methods can deepen our knowledge on the combustion chemistry of these fuels. And also advances in kinetic modeling can improve our ability to predict the combustion chemistry of these fuels. And advances in regulating combustion chemistry can also support the applications of low carbon fuels in power machineries without being affected by their different combustion characteristics from those fossil fuels. In the future, we need to develop and get more advances in the experimental and diagnostic methods that can provide us increased knowledge on the combustion characteristics and chemical structures of low carbon fuels on the relevant conditions in power machineries, which are very important for the validation of kinetic models. And a deeper understanding of the combustion kinetics of low carbon fuels, especially more accurate rate constants for important elementary reactions, is desired to develop highly predictable and widely applicable kinetic models of these fuels. And also we need more investigations on the regulating strategies for the combustion of low carbon fuels, especially for the solution of trade-off behaviors between the combustion enhancement and the NO emissions. And this will help us to facilitate the application of low carbon fuels like ammonia and biogas in power machineries. I would like to thank the funding support from my funding agencies and also collaborators from other groups, and also my students and postdocs in Shanghai. And here are all my presentations, and thank you for your attention. I would like to further discuss with you. Thank you.
Thank you, Professor Li. Thank you for a very interesting talk. And today I see 3 questions in the chat. The first question is from Professor Go, which is more about ammonia itself. So is an ammonia economy being thought about, or will ammonia remain a few limited to locations where it is available as a byproduct of chemical production plants? And where the use of ammonia as a fuel compete with the need for fertilizer for food production?
Yeah, thank you. This is a very good question. And I think that for ammonia, because it's actually, we all know that it's very easy to be transported compared with hydrogen. So if we can produce it, for example, in some chemical engineering industry or in other locations, I think we can easily transport ammonia much easier than hydrogen. And I think that for ammonia in the future, if we will use it as a future fuel, I think it is not only in chemical engineering industry, but also will become an energy storage agent. So it can also be generated in some solar energy station and also wind energy station, and this will also let us to transport it also. So I think this will be not a problem for the future applications of ammonia, in my opinion. And for the second question, and actually, this also always concerns about the competition with the renewable fuels. This also happens for biofuels if we competing with our food production. And then for ammonia, we also know these fertilizers to the food production is also the concerns. But this also depends on the technology and how people can better generate ammonia. If we can find a more efficient and also less energy consuming method for ammonia, and I think because people have count for the ammonia production, and we found that it's mainly just the just the consumption of electricity, and therefore the price will be dependent on electricity. So for the future era, for future scenario, and I think it's mainly just for the renewable energy, renewable electricity generation will make it happens and will make the problem less influential to our other needs. Yeah, thank you for the question.
So the next question is from Professor Zhu. So NO in ammonia air combustion is at 100 to 1000 ppm level. And NH2 concentration is low as well. So NH2 plus NO reaction rate should be very low compared to H plus O2 branching. Do you think NH2 plus NO is the most sensitive chain branching reaction even in ammonia air combustion, or just in ammonia plus NO flames?
Yes, this is a very good question, and I think this reaction mainly when we're talking about it, it's just with conditions that the NOx reduction, because in both thermodynamics pathways and also in ammonia combustion, we need to consider about how to reduce NOx. Under these conditions, this reaction would be very important. And in ammonia combustion, of course, the hydrogen plus O2 reaction is the most sensitive reaction for the laminar burning velocity and also for the flames. Then if we go to the, for example, stoichiometric and the richer conditions, and because ammonia has a leakage problem, it is not consumed totally, and NO is also forming with high concentrations, then you can get a very strong interaction between ammonia and NO, and this will strongly influence the prediction accuracy of a kinetic model on the, especially the reduction window of NO in ammonia combustion. If we are just looking at the equivalence ratios, it's slightly higher than 1, it's 1.1, 1.2. And this accuracy is strongly controlled by the NH2 and NO chemistry. And therefore, the purpose of our work is, the motivation of our work is just to generate conditions without H plus O2 reaction that can make NH2 and NO reaction quite sensitive and easily validated. And that's a motivation. And yes, Professor G is right. And that is reaction, H plus O2 branching definitely will be the most important chain branching reaction in the oxygen combustion, in the combustion with oxygen as the oxidizer. But then the purpose in the motivation of our work is go to see the denox or the NH3 and the NO reactions on the specific conditions. So that's considerations. Yeah, thank you.
So the last question is from Professor Wright. How important is the NO plus H2O to NO2 plus OH reaction that you do not mention?
Yeah, we actually didn't find this reaction very important under the conditions we are investigating, because under flame conditions, HO2 is less produced compared with OH and other radicals. And therefore, this reaction is not so important compared with NH2 and OH reaction and so on. And therefore, we NH2 and NO reaction and also other reactions. And therefore, we can't answer that this reaction, how the importance of this reaction will be in our system, also in other systems, because this reaction was less mentioned compared with the NH2 and NO reaction in the ammonia and the NO interactions. Thank you.
We have also a new question from Shanglong Zhu. Thank you very much for your nice presentation with very much details. I have a question about the synergy between ammonia and hydrogen on page 43. Is this also validated by experiments or actually applications? Recently, there was an interview of Professor Robert Bastians from the Netherlands promoting the mixing of hydrogen and ammonia from the flame speeder point of view. However, if the synergy is there, NOx emission would be harder to reduce. How do you think about this issue?
Yeah, thank you for the question. It's a very good question. And this synergy is not a single reaction. It's actually in a reaction network. And here we can see that this is NH and this is H. NH forming NO mainly depend on the concentrations of O and OH. Therefore, if we have a lot of H, H plus O2 can give us a lot of O and OH. And this can make the oxidation of NH very efficient. That will causing stronger formation of NO. And yes, this is a problem that if we're burning we're using hydrogen to enhance the combustion of ammonia, and this synergy will happen, and because we have a lot of NH and H radicals simultaneously, and this will, especially at some specific conditions, the blending ratios. And therefore, we have to consider that we can use some strategies for first, because actually if we just using percentage of hydrogen up to 70%, actually the laminar burning velocity and also the combustion intensity is already very strong. And maybe we do not need to use so high, then we can use lower. And as we can see, if we just go to the, for example, 40% or 30%, and this is moderate addition of hydrogen, and also the acceleration of the combustion intensity is already very adequate, and here can slightly prevent compared with 70% blending ratio. And also other strategies need to be considered to avoid the trade-off effect of the combustion enhancement and also the pollutant emissions. And so we can hardly use one single strategy to control both the combustion reactivity and also the pollutant emissions. Yeah, thank you for your question.
So the next question is from Professor Lee. Have you measured the ammonia emissions and the effect of hydrogen blending on ammonia emissions?
Yeah, unfortunately we haven't, because we now for ammonia combustion, we are mainly focusing on the enhancement strategies. So we're using laminar burning velocities, and also we're using the swirl flames. And now currently we can hardly measure ammonia. So we want to together with other methods like FTIR and other methods, we want to measure ammonia. Then we can give the answer. Yeah. Thank you.
We have also some questions in the Q&A. Do you see the country's carbon neutral targets realistic? If they are not quite realistic in terms of investment for clean combustion research, do these unrealistic targets may lead to loss some opportunities about possible advancements in the future?
Yeah, this is a very good question, but also it's related to the policies. I'm not the best one to answer this question, but I can share some of my considerations. Yeah, it's definitely for any policy or any strategy of a country will be doubted or will be approached by different from different views. But I think for the Paris Agreement, and I think with almost 200 countries signed it, it's a common sense that people need to control the carbon emissions. And it's not only a strategy that is related to carbon emissions itself, but also related to climate and people's humans' future. So if we want to predict it's realistic or not realistic, I think maybe from this just 5 or 6 years, it's not very easy to make these predictions. But I think this can help, definitely helps a lot of industry to improve their techniques, and also it can help people's who is really worried about the world's future with this thinkings. Then with these targets, we can do it together to make the world better. I think that is not a bad thing actually, and we can just consider deeper about this targets or these strategies. But I think since almost all countries now agrees that we should control it, and therefore it doesn't have the second question. That's we don't have possible advances. I think since the especially when we are looking into the renewable electricity generation, for example, from solar energy. I think nowadays in China, the price can be controlled to almost 0.1 Chinese yuan per degree. I think this is quite cheap, and therefore if people can better develop the technology, then the low carbon fuels and also for the low carbon energy systems can work quite well. So I think that may not cause big problems to the possible advancement. And also I know that in Saudi Arabia, the price of the renewable or solar energy is much cheaper than China. So I think it's in many countries of the world, people can afford these countries can afford renewable electricity. So this may not lead to some loss of opportunities in possible advancements in the future, I think. Yeah, thank you for the question.
So thank you, Professor Lee, for the very nice answers. And I remember when you visited me before several months, we have also a lot of interesting discussions regarding the exciting results. And as Professor Dibble wrote in the chat Q&A, thank you for most exciting and enjoyable presentation. So if there's no other further questions, I think we will close the Combustion webinar today.